Okay, so I'm going to switch you to, I'm just going to mute everybody. And I'm just going to flip over to the shared screen. And we'll take it away from here. Okay, so we're here to basically cover the MET section of the pilot exam. If you don't have a copy of the syllabus, download it. But basically, I'm going to pretty much, I've reorganized my talk to basically pretty much follow the steps of the syllabus. So we'll see how much we get through sensibly in 45 minutes. If I can open up the mics for questions at some point, I will. But as I say, I'm not going to try and do all of this in 45. This will definitely get spread over a couple of weeks, and we can also have, like, after that, a question and answer session as well. So let's go to the other one. All right. So I've got basically I have a PowerPoint, which is the basis of the talk. And anyone who wants it, if you drop, I can probably just drop it onto Telegram or contact me directly, and I'll send you a copy of it. Anyway, so first point is to understand the relationship between wind direction and areas of high and low pressure. The key points of this are that air flows towards low pressure and away from high pressure in the northern hemisphere. Wind blows in a clockwise direction around highs and anti-clockwise around lows. So this diagram basically illustrates it here. So you've got the area of low pressure. Oops. Okay, one more person just joining. So here we've got the red arrows going up, which is the area of low pressure. So this is rising air. Descending air, so basically a warmer air, the reason it's red is because it's warmer air, so rises. It goes up. Your descending air gives you high pressure. And it's just a very basic concept. If air is going up, you have low pressure. If air is descending, you get high pressure. And the air will flow from regions of high pressure to low pressure. It's just basic physics, but air flows in that way. So air will go from high pressure to low pressure, and because of the Coriolis force, it will then turn as it goes, and then so you then get this motion of around high pressure you get clockwise direction winds, and around low pressure you get anti-clockwise. So that's just your basic principle. I've thrown this diagram in. You don't need to know this for the exam. I've just basically put it in. Oops, sorry, a couple of people waiting. Let's let them in. Okay, got two more people just joining. So yeah, so it's there for information and to illustrate how Coriolis works, but you don't have to understand how Coriolis works for the purpose of the actual exam itself. Anyway, next diagram on here should be Stephen joining. So I've got two more trying to join. Let's let them in. There we go. So for those who just joined, we're basically still on the first step here, which is looking at this principle of, not that principle, this one, that air flows from high pressure to low pressure. Low pressure is where it's air going up, high pressure is air coming back down. And you basically have this basic concept, which is you have high pressure here on the left-hand side, going to low pressure on the right, and the difference in the pressures creates this sort of gradient force which drives the wind. Because of Coriolis, the way the Earth spins, it doesn't go in a straight line, it ends up curving away. And so then you'll start to see this pattern where it goes from high to low, starts to curve down. Now it's going to go anti-clockwise around lows, and it's going to go clockwise around high. That's basically all you need to know on that. There is there's a little law called Ballard's law, which if you're in the northern hemisphere, why is this person not coming in? Sorry, someone called Steve who keeps trying to, I keep letting him in and he keeps bouncing back out again for some reason. So in the northern hemisphere, the person standing with his back to the wind will have high pressure to his right and low pressure to his left. I.e., you can always remember it's low on your left. Anyway, it's quite interesting. You can actually do it next time you're on a hill and the wind's blowing. You'll get, you can actually exhibit this yourself. Back to the wind, and you'll see there high pressure on the high pressure to his right hand side and low pressure to the left side. Okay. So gradient wind. So again, this is basic idea. Wind flows from high pressure to low pressure. When it talks about isobars on here, it's talking about on a synoptic chart. When you're above 1,000 meters, so you're away from ground effect, wind direction will follow the pattern of will blow parallel to isobars. As you get closer to the ground, and when you're actually down at ground level, ground friction will change the direction of the wind. So it's when the wind's going around a low pressure system, it doesn't go. If you look at the isobars, it'll actually bend about 30 degrees away from that in towards the center. So person waiting. And we'll look at that a little bit later because we have to look at synoptic charts later. We'll see that effect on there. But when you're asked to look at wind direction on a chart, you have to bear in mind you look at the isobars and then you add a factor of about 30 degrees to get the actual wind direction. Okay. Oh, another one. There we go. Howard Smith. Okay, it's got Howard joining. Cool. Okay, so this is all to do with this first point, which is just understand the relationship between wind direction and areas of high and low pressure. So I think that's fairly straightforward. Let's get on to the next bit. So the next chunk on this is to understand fronts. On the syllabus, it's to be able to describe in detail a cold front and a warm front, typical clouds, conditions, pressure changes, and wind changes. And what you'll find on this is you do need to know this in a reasonable amount of detail. You will get, typically there are questions on it where it will describe certain conditions and it will say, is this a cold front or is this a warm front? This is, again, the first bit is like a bit of trivia. You don't need to know this guy was the first person who named it, but it's where the word front comes from. Basically, they were named 1919, and it followed on from the First World War, and the idea was you had this battle going along your fronts, and that's where they came from. So, it says there are three main types of weather front. These are shown on synoptic charts. In case you don't know, the word synoptic simply means a summary of the current situation. There's nothing more fancy than that. In weather terms, it's the pressure, pattern, fronts, wind direction, speed, etc. So, cold fronts. So cold fronts have this. So here you can see the cold air coming in from the left-hand side, and so the cold front is meeting warm air. So cold air is coming in. It's going to drive the warm air up over the top of it, and you'll get. So it divides cold air from warm air. They move quickly. If you've been, I don't know how many have actually been on the hill and you've looked at on a day when there's a front coming through, and the cold fronts they arrive fast. They don't take a long time to get there, and I've seen pilots get caught out by this, where what they forget about as well is this point here, which is expect a squall as the front passes just ahead of the front. So you've got this fast moving air driving into this warm air, and you get this gust front ahead of it. And you'll notice that if you're on a hill and on a day when there's if you have a look at a chart, figure out when a front's coming through, go out, see if you can time it, and you'll notice the increase in wind speed just before the front comes through. And so if you get caught by that, you're in really shitty air. It's not good at all. So let's have a quick look. On a synoptic chart, the cold front is this blue line with the spikes on it. So the presence of cold air front means cold air is advancing, pushing underneath warmer air. Fundamentally, the mass of cold air is heavier or more dense, so the warmer air goes over the top of it. So these are your main points, and again, this is the sort of thing after this to go through, take a look at, and get to grips with it. Just sort of test yourself on whether you can remember these factors or not. So the main point about cold fronts divide cold air from warm air ahead. They have significant cloud development, cumulus nimbus, few halving. In other words, you don't get a lot of predictions of it. They just hit. They move quickly. They pass in a matter of hours. You can expect a squall. The wind will veer as the front passes. So back, veer means it's going away from zero. So it'll go like from 0 to 15, 20, 30 degrees. Back means it would, if you're at 30 degrees, it would go like back to 0. So veer is going in a clockwise direction. Back is in an anti-clockwise direction. For the easiest way of looking at it. Precipitation is likely as the front passes, very likely. But you then get this clear band as the ground warms and dries, and the buildup of cumulus, with significant risk of overdevelopment due to unstable moist air. But this factor here is where often you'll see a lot of cross-country pilots looking for cold fronts, or a day when a cold front's coming through, because on the day afterwards, you will normally get like really good cross-country conditions. The air's a bit unstable. You've got cumulus clouds. You get good climbs. It's good cross-country weather. So you'll often see on forums different things. People talk, oh, it's a cold front coming through, brilliant. And it's one of those classic days for going up to like Thames Valley, going like from Coombe back down to the coast, because inevitably the wind's swung around. It's gone onto a northwest. Lines up nicely, you've got great conditions, and you can go off and fly. Okay, you don't need to know that for your exam, but it's just useful for actual being on the hill, using that data. Okay, warm fronts. So warm fronts are symbolized by this line. So the presence of a warm front means the warm air is advancing, so it will now rise over the cold air. Same principle, the cold air drives underneath it on a front, the warm air will go over the top. Exactly the same principle. So here we see like a warm front coming through, and what you'll often see in advance of that is the high cirrus. So you get a day and you look up and you see lots of cirrus coming through, then it's usually a sort of fair prediction that a warm front is on its way. So then you get this build up of cloud layers of a warm front. It starts with the cirrus, then you get the cirrostratus, altostratus, nimbostratus. So this is where you're getting this blanket of cloud with rain that follows on with it. So very different from a cold front. So it divides warm air from cold, has significant harbinger is just something that tells you something's coming. So with warm fronts, you get high cirrus, halos around the sun, stratus cloud, lowering cloud base, rain. And as completely different from cold fronts, they move slowly. So a warm front can take days to pass through. And that's those conditions you get where you've got grey cloud, low cloud base, drizzly, horrible, crappy weather, and a warm front has come through. So again, these you just need to, however you learn things, sort of run through these. I don't know how it is you memorize stuff. Just get used to looking at the diagrams, going through whatever it takes to write them down. I'm going to mention these. It's not on the pilot exam, but just for completeness. So the other fronts you get are occluded fronts. Again, no, not part of the exam syllabus, but it's included for completeness on fronts. Because particularly when you start looking at synoptic charts, you'll see this a lot on a synoptic chart. You'll see this mixture of cold and warm fronts, which is an occluded front. And it's basically where a cold front catches up with a warm front, not just warm air, but you've got a warm front going, cold fronts go faster. So it's quite common to get occluded fronts because they'll catch up with them. And then you get this phenomena of, this is your sort of line of the warm front, this is the cold front. It comes through, catches, and it basically forms this area of warm, moist air in between them. So, just that there. Okay. This one, the next point is be able to identify some common high, medium, and low cloud types and give their approximate heights. I do have a separate chart on this, which I meant to put on the screen, which I don't have, but I will send it out to you guys if you want it. But basically, your different cloud types. You've got cirrus, which is your high level cloud. And again, so it's made of ice crystals. You get no precipitation from cirrus clouds. All the cirrus ones are basically too high for precipitation to occur. You're not going to get rain at 25 to 30,000 feet. It doesn't happen. I'm interested in those particularly. Cumulus, your mid-low level convection clouds. Sorry, one more person needs to join. Okay. I'm not going to spend too long on clouds because there's so much that covers it. I'm going to quickly see. I need to drag over something on it. Bear with me 1 second. I'm just going to quickly copy over from one place to another. Where is my image? Yeah, here we go. Right, give me 1 sec. I'm just going to drop this one. Okay. Just pop this open. This is just a quick diagram. Right. There we go. Okay. So this is from the Met. As you can see, it basically gives you everything you need, the basic stuff you need about clouds. So here we've got down the right-hand side approximate height in meters, the high level, you've got your cirrus, cirrocumulus, cirrostratus. You can see you've got your cunimbus, which starts here from a very low level and can run all the way up to 18, 20, 25,000 feet. Anyway, so I'm not going to dwell too much on that. It's something you can take a look at. It's easy enough to find information on. and it's easy enough to, to have a look at which ones have rain, which ones don't. It's not too technical, so we'll leave that to one side. Right, so the next bit we have, crap on clouds. Okay, so this bit I'm going to spend a bit more time on, which is these two sections here, which is fully understand convection, birth and development of a thermal, through to plotting the progress of a thermal given the environmental lapse rate, understanding and be able to use terms such as stability, instability, veer, back. We'll cover what those are now. So, lapse rates. So lapse rates are just to do with how the change in temperature in air in different conditions. Bouncing out. To do with the change in temperature. And I'm just going to jump a bit between this and how clouds work. So the basic principle is that air will rise because it's warmer than the surrounding air. That's like the fundamental basic concept which underlies thermic activity, cloud structure, and everything else. And there are then, and basically a parcel of air, if you imagine a parcel of air leaving the ground, it's at ground level, it's considered to be dry. And you'll come across this term, which is dry adiabatic lapse rate. Adiabatic is just means no added or removed heat. It's a contained system. So we have this theoretical parcel of air, and it's called dry because it's not saturated, not because it doesn't have moisture in it. That parcel of air rises, and as it rises, it will cool. When its temperature drops to dew point, then the moisture in it then will condense and form water droplets, and at that point it's considered saturated. So it's in one or two states. It's either dry or it's saturated, as technical terms. So when you come across this, there is no in-between stage. It goes, it's dry, saturated. That's it. As long as it's dry, it then cools at this rate of 3 degrees C per 1,000 feet. If you're in metric, convert it, but I'm going to stick with these units. Once it becomes saturated, in other words, the water in it has condensed, it's now saturated, you've got water droplets, it now cools at half that rate. It only cools at 1.5 degrees C for every 1,000 feet. Environmental lapse rate on average is 2 degrees C per 1,000 feet, but it says that varies widely. So with environmental lapse rates, what you'll actually get is like a set of figures or a line where it says at this height the environment temperature is this, at this height it's that, at this height it's this, and you'll get a graph. So which I'll just have a look at now. But I'm just gonna, before we go on to that, I'm just gonna very quickly, you should be able to, if anyone's got any questions on this at this point, you should be able to unmute yourselves and ask. It's just, this is quite a key thing. If anyone's not quite grasping it, let me know before I crank on to the next bit. I think you can unmute. No, I'm just going to what I'm going to do, I'm just going to unmute you all very briefly so your mics are open. You can hear all the coughing and spluttering. So if anyone's got any quick questions, far away at this point.
Hi, John. I have a quick one.
Yeah.
Can you hear me?
Yes, I can.
Brilliant. So we got, I'm just trying to get the 3 degrees drop every 1,000 feet.
Yes.
Dry adiabatic lapse rate.
I can't get the sound to work on this, so I have to do it through there.
Sorry, we're assuming that that occurs anyway within the 2 degree drop of the environment.
Okay.
So I'm guessing because the air is rising.
Oh, 9 minutes later.
That air, because it's just expanding.
Just give me a second. I'm just going to mute everybody, then unmute you, so I don't get all the background of everyone. Great. Okay, you're unmuted now, so I won't. You can talk. We won't get everyone else in the background.
Brilliant. Thanks, John.
Yeah.
It's step science, by the way. I don't think I've labeled my phone. I'm just trying to get the idea of this. So the rising air cools at 3 degrees per 1,000
Correct.
feet. And it's assumed it does that.
It just cools at 3 degrees per 1,000 feet. Literally, regardless of what else is going on, it cools at 3 degrees per 1,000 feet.
Around it being 2 degrees drop per 1,000 feet.
Yes, let me go on to. Let me. I think I'm going to answer your question.
I'm assuming that I don't sound like a Dalek.
Yeah.
Yeah, I didn't hear that, but I'm assuming that the difference in temperature occurs because of the rising air cooling because it's expanding, and that's why it goes.
It's to do with, we can get into the particle physics of it, which I'm not going to. Just for now, keep it simple and just take, yes, it does cool at 3 degrees C. We can get into the physics of how fast the particles are going and why, you know, at this speed, it's this temperature, at this speed, it's that temperature.
You don't need to know that.
You don't need to know that. Keep it simple. Just take it that it will cool at 3 degrees C for every 1,000 feet it goes up. By all means, read more.
Perfect. Okay.
Keep it simple for now. I like to. I'm just going to mute you down. So, yeah, I'm not. I don't want to. One of the things on this is it's very easy to get sidetracked into stuff that you actually don't really need to know, and isn't actually going to help you. If you want to find out about it, do. But it's not essential. So let me just go on to this next one. That's the same one. Next one, John. There we go. All right. So basically, this the blue line on here represents the environmental lapse rate, represents the temperatures at different heights. It's purely demonstrative. It's not. Don't take it out. We'll look at some actual ones if I get time in a minute. So a thermal rise is because it is warmer and thus, to answer your question, less dense than the surrounding air. The greater the difference, the faster the rate of ascent. Shall I explain in a second? So any thermal will continue to rise until its temperature is equal to that of the surrounding air. So yeah, it's rising. As it rises, it cools. As long as it's warmer than the surrounding air, it will continue to rise. Once the two temperatures balance, it will stop rising at that point. So we're going to run. Oh, okay, we ran out of time. So we're going to. I only get 40 minutes on this one. If you guys want to do a bit more on this evening, I can quickly drop onto the two chat groups. The next log on. Let me just quickly get a quick survey of what you want. I think it'd be good to do a bit more on this. Just going to unmute you. Quick survey. Do you guys want to do a bit more? Like in about once this will finish in about 10 minutes.
Carry on.
Right. Yes. So once this wraps up, give us 10 minutes. I'll drop something onto the coaching group and the 3 Telegram groups, and you can log back in again. Okay.
Thanks.
Yeah, thank you.
Great, good. Again, it's amazing how fast this goes. So, but this is the key area. So here we're just going to take a look at this in a bit more detail. So here on the blue line is our environmental temperature. The red line is going to be our parcel of air rising. This is our theoretical thermal. So in this case, we've got here a thermal trigger temperature of 21. Thermal trigger temperatures vary depending. So this is purely theoretical. We're taking it there. You can see between 19 and 22, 21 degrees. It's going to be at that temperature. It's going to release, and then it's going to rise until its temperature is dropping as it rises. Here it meets the environmental temperature, so now it stops rising. It's another diagram. Again, there's our environmental rate here. So here's our thermal rising. and it's cooling at this 3 degrees per 1,000 feet. In this case, basically the distance between the environmental rate and this line, the gap, is thermal strength. So the wider this gap, the stronger thermal. This is a very unusual situation. When we look at some real diagrams, you'll see it's nothing like this. It's usually the other way around. So it's actually usually narrow at the bottom and actually expand, gets stronger as you go up. This would be like an insanely strong thermal near the ground that suddenly drops off and gets weaker as you go up. Not going to happen, but it's just for demonstration purposes, it works. So again, here, packet of air leaves the ground, it will keep rising, it just misses the inversion and it hits it here. So it will stop rising at this point. Here it goes on further, and again, very strong lift here, weaker, 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 similar, weak, 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 all the way up to the top. And as I say, that's highly theoretical. You'll almost never ever get that. It's just for the purpose of this diagram. But that's the basic principle of that. So this explains it a bit more detail on the last one. So a trigger temperature of 26 degrees. What's weird here is that if that's actually your ground temperature, it's rare that you need a trigger temperature that much higher for a thermal to release. It's normally much closer to the ground temperature. Which again, I'll bring up some actual diagrams in a minute. We'll take a look at those. So let's just leave it for a second. I'm just gonna now we're gonna look at a real diagram. So this is called a tepigram or a skew T chart, whatever you want to. They're basically much the same thing. And the way these are laid out. So in this case, just to clear it up, the red line is the environmental lapse rate. So this is basically where the Met, different areas, they take soundings, they send instruments up, they'll measure at different levels what the actual environmental temperature is, what the actual air temperature is, and on the basis of that, they'll predict for the next coming days what it's going to be at different heights. So what you'll then get is this environmental rate. The blue line is the environmental dew point. Don't worry too much about that. Our main interest here is this red line, which is our environmental lapse. I'm gonna just the various lines on here give us our saturated, dry adiabatic that we were talking about, and the dotted line you see here is a thermal that's being released. Now this is a much more realistic example of what actually occurs, and we'll zoom into it in a second, have a look at that in detail. But here you see that the difference between the dotted line and the red line lower down is quite small, and then as we get towards this area near the inversion, it expands, and you get that what's known as cloud suck. You're getting close to clouds, suddenly it opens up. You get this lift. But this is way more realistic, where it's like, yeah, looking for thermal. You know, you crank your way up, start to get high, and suddenly it kicks in a bit more. So let's just go to this one. So this is like zooming into that. So here we have the red line again, environmental lapse rate. The dotted line is our predicted thermal. So it releases from the ground here. It then, these lines you see going at 45 degrees from right to left. This is our lines of dry adiabatic. So these are the temperature drops associated with that. So this line is following it. It releases, it will now follow that cooling. So if you took temperatures here, you'll find this is dropping at 3 degrees C per 1,000 feet. So it will continue to rise on the dry adiabatic until its temperature drops to dew point, which is what this line here is giving us, the dew point line. At that point, it becomes saturated, and it will now rise at the cooling rate of 1.5 degrees C. So it's now on the saturated line. So that's just want to. So that's got nothing to do with inversions or anything else. It's purely that it rises, it saturates, it now rises on the saturated line. So this is dry rising, saturated rising. We've got about 2 minutes left of this meeting, so I'm not going to go into another slide at this point. But that's we'll pick up at this point. But this, so where it switches from dry to saturated is cloud base. Okay, so at this point, it's condensing, so it's the area is no longer dry, it's droplets. Droplets are bases of clouds, so you see cloud base. So cloud base is the point where it saturates. The cloud top is where it will still rise. So at this point, it's still cooler, so it's still warmer than the surrounding air temperature. So it's going to keep rising, keep rising, keep rising until its temperature becomes the same as the surrounding air. So now it will stop rising. So that's your cloud top. All right. So cloud base, where it saturates. Cloud top is where the saturated air has now, the temperature, it's basically cooling, and it's now the same temperature of the surrounding air, so it can't rise anymore. It's just basic physics. It's no longer warmer, so it can't keep rising. Okay, we've got 1 minute left. This will suddenly cut out, so rather than that, I'm going to end it. Create a new meeting. If you just quickly jump onto Telegram, you'll get the new ID and password. I'll drop it onto coaching group, red ribbon group, and the chat group. Okay. But don't rush. You can go grab a cup of tea or something. What time's it now? About 8:40. So we'll start again in 10 minutes at 8:50. Alrighty. I'll see you in 10 minutes. End the meeting.